In this video, we're going to look at making a buffer using a diprotic acid or base. We're going to stick with alanine just to keep things simple and use the same pKa values that we've been using previously. With the diprotic buffer, the way we can think of it, right, we have our three different species that are present, that are possible for our diprotic acid/base. In the case of alanine, we have the fully protonated, intermediate, and fully deprotonated forms. And when we make a buffer, we can think of the buffer as consisting of either one or the other of pairs of these. So we can have one buffer that would exist between H2A plus and HA. When those two are present in solution, we're not going to have a lot of A minus that's left in the solution, and we can essentially sort of ignore it. We also can make a buffer that consists of HA and A minus. For either of these, if we want to find the pH, we use the Henderson-Hasselbalch equation. And we'll have two different Henderson-Hasselbalch equations, depending on which pair we're going to be looking at. These two buffering systems will work in different pH ranges. So for example, if we have H2A plus and HA as our buffer, the pH will be equal to pKa1 plus the log base 10 of concentration of HA over the concentration of H2A plus. So base over the acid, right? And so that's just the Henderson-Hasselbalch equation just applied to this particular system. Otherwise, it's going to look very similar to a monoprotic system. So we'll have when the concentrations of these two are equal to each other. At that point, the log term goes to 0, and the pH will just be the same as the pKa value. Similarly, for this pair, HA and A minus, we can write a separate Henderson-Hasselbalch equation. pH equals pKa2 plus log base 10. And here our base again goes on the top, A minus over HA. And the key here is to keep track of which pKa value goes with which one, right? So it's always, in whatever Henderson-Hasselbalch equation we're looking at, the value of pKa always is the value of the acid that's in the denominator of the equation that we're looking at. So that's why the equation on the left has pKa1, because it's the first loss of the first proton, and one on the right has pKa2 because it lost the second proton. But the key thing to realize is, as we calculated at the beginning, when your primary species present in solution are the red, right, are H2A plus and HA, the concentration of A minus is basically negligible, right? It was very, very small as we calculated in the first couple of videos for this chapter. So if we're dealing with these diprotic buffer systems, which species are going to be present sort of depends on what pH range we want to look at. So for this particular system, coming back to the pKa values for these, our pKa1 is 2.34. So a buffer made of H2A plus and HA would sort of have its maximum buffering capacity at pH of 2.34, whereas pKa2, the pH is pKa2 is 9.87. So the pH for this second buffer system, composed of the blue species, the HA and A minus, would have a pH much higher. As we're thinking about these buffers, right, if we want a specific pH, then we need a specific ratio of these species. And similar to with the monoprotic buffer, we can start with one form of this and use strong acid and strong base to transform it into another form. So you'll get a chance to work with this in your homework. But for example, say we have just neutral alanine that we can find, and we'd like to prepare a buffer close to 2.4 or whatever. We'll need to add acid. So let's say we're preparing buffer near pH equals 2.4. That's close to this pH value down here. So we need to add acid to convert some of the HA to H2A+. And we can figure out what ratio we need by using the Henderson-Hasselbalch equation. All right, so that's it for diprotic buffers. Very similar to monoprotic species, just need to recognize that you'll have specific pairs of conjugate acid-base pairs present at different pH values. And we can get sort of the range of pH values we'd expect those to be at by using the sort of middle point where we have equal concentrations of them. There'll be a spot in between. So between pH 2.34 and 9.87, we primarily just have HA, and it doesn't make a good buffer. So yeah, it's just going to depend on the specific diprotic system that you're looking at, what those specific values are.